Hi, in today's video, we want to look at the concept of vectors. So we're going to be looking at the addition and subtraction and also the multiplication of vectors underneath this series. But for the sake of this video, we'll only be looking at the addition and subtraction of vectors. Then in subsequent videos, we'll look at multiplication of vectors. Also, underneath the addition and subtraction of vectors, we're going to be looking at the graphical approach to solving questions on addition and subtraction, especially as vectors is concerned, and also the resolution of vectors. But in order not to make this video extremely lengthy, so we'll only look at the graphical approach. We'll look at the triangle law of vector addition and also parallelogram law of vector addition. Then in a subsequent video, we look at how to resolve vectors into their various components and use them to add or subtract two quantities together. Why the need for vectors? So far, we've looked at motion in one dimension, where we talked about several quantities, out of which we talked about displacement, we talked about velocity, we talked about acceleration, and then we said when we talk about velocity, especially when an object is changing its position towards the right, then the positive sign should describe, or it's enough to tell us about the direction of our velocity. And then when the object is changing position towards the left, then the negative sign will just account for its direction instead. But then, like, since we have objects moving in space and planes, then definitely we don't have the luxury of saying if an object is moving towards the right, then the direction will be positive, and if an object is moving towards the left, the direction will be negative. So hence the need for vectors. So we're going to be looking at the basics, how we describe an object's location, which we did in the previous video. We made mention the Cartesian coordinate system. We say we have an object located in a plane, an XY plane, then we can describe its location using an ordered pair of x, y. So we're going to be looking at the second method, or the second way of describing an object's location, and then we'll pick up from there where we'll look at the vectors proper. So suppose we have an XY plane like this, in this format, and I have a point located here. If I have a point located here, the first way, which we treated in the previous video on how to describe this point, because this is my origin, point 0, and this is the positive x-axis, the positive y-axis, then I can say from this point, if I trace this line down, I'll have an x value. If I trace this line like this, I also have a y value. So I can describe this point using my x, y. We did this in the previous video. So how else can we now describe this point without using a Cartesian coordinate system? Now we can make use of our polar coordinate system to describe this point. The polar coordinate system is also a popular way of representing a point in a plane. And for this, we want to write the magnitude or the length of our line, and then the angle it makes with our positive x-axis. Now, if this is my positive x-axis, this will be my negative x-axis. This will be my positive y-axis, and also negative y-axis. So if I want to describe this point, like I said, using my using the polar coordinate system, so what I simply need to do is to take a ruler and draw a line to where my point is located at, and take my ruler and measure it. Once I measure it, I'll have the value, let's say r. So you can call it anything. Some textbooks they use L, some textbooks they use D. It doesn't really matter. For the sake of this video, we're going to be using r. So r just signifies the length of my object's location, or how far my object is from the origin. Now, this r alone is not enough to describe my object's location, because if I'm having r here, I can have r in the second quadrant like this. Imagine I were to have a mirror that just reflects my object's location. So I can have r here, I can have r coming down, I can have r in this fourth quadrant. So how do I differentiate which of the r's I'm referring to? So hence the direction. my polar direction. So, and this is the angle it makes with, or my line or my R makes with the positive x-axis anti-clockwise. So this is my positive x-axis, this side here, and then I'm moving anti-clockwise. So it means this is my theta polar. Now I can convert from the polar coordinate system to the Cartesian coordinate system. So, and that can be done using our Pythagoras theorem and then our knowledge on SOHCAHTOA, that is the trig ratios. So for Pythagoras theorem, if I know the x value, if I know the y value, then I can get the r value by simply saying r is equal to square root of x squared plus y squared. So I can use this, once I know the x, I know the y, I can use this to find r. And if I want to find my direction, if I want to get the direction here, I will simply say the tan of the reference angle, reference angle will simply be equal to y over x. So we got this from our knowledge on SOHCAHTOA. Remember, if we are saying SOHCAHTOA, let's just write it here, SOHCAHTOA. So tan means opposite over adjacent. In my triangle here, this is my opposite side, which is the y side vertically from my origin, or the maximum vertical displacement from my origin, and then the x is the maximum horizontal displacement from my origin, which is the adjacent. So if I take the ratio, then I'm talking about my tan ratio. Now, why is it that I mentioned tan of reference angle? Why didn't I just put theta polar inside of this directly? It's because we have different polar angles. Now, for the first quadrant, you can see that my reference angle would always be equal to my polar angle. But let's assume that I have a point located in the second quadrant this time around. I have a point located in the second quadrant. Now, if I decide to draw a line like this, of course, I'll be having R also. Now, if I decide to complete my triangle, remember what we said, our theta polar is always from the x, from the positive x anti-clockwise. So it moves like this. So this is my theta polar. But if I complete my triangle, then my triangle looks like this. So this will be my y. This also will be my x. Then definitely I have a reference angle here. So let's call that reference angle, let's call it alpha. So if I want to get r will always be equal to square root of x squared plus y squared. But my direction, my theta polar would be different because theta polar, I can't get theta polar directly. So first I need to get this reference angle, then subtract it from 180 to get my theta polar. Why am I subtracting from 180? We know that the angle on a straight line, or the total angle on a straight line is equal to 180 degrees. But look at my theta polar, I'm coming from here, but I'm stopping here. I'm not completing 180. So this other part here, I can simply subtract from 180 to get my theta polar. So my angle or to get my theta polar, I can simply say tan of alpha reference, if alpha is the name given to my angle in the triangle I have in the second quadrant, will simply be equal to y over x. And after getting my alpha reference, I can simply say 180 minus alpha reference must be equal to my polar angle in the second quadrant. Now, if I have an object located in the third quadrant, let's say at this point here, again, complete your line like this. So let me draw that properly. So complete the line to the origin, and then complete your triangle like this. Okay, so now which angle am I looking at? I'm looking at this angle. So let me call it beta reference. So let me make a space on the right so that we can get our what's it called, reference angle, and then our r. So r again will always be equal to, I'm looking for r, since I have an x value here, I have a y value here. So r will simply be equal to the square root of x squared plus y squared. And then my angle theta polar would be equal to 180 plus beta reference. So why is it 180 plus beta reference? If I complete my triangle, my opposite side still remains y, my adjacent remains x. And then the angle I have in between, we said it is beta, my reference angle. So tan of beta reference will be equal to y over x. And then beta reference must be equal to tan inverse of y over x. After getting this, we add it to 180 because, of course, we know the angle on the straight line is 180 degrees, but then we're not stopping at the straight line. We're moving slightly a bit downwards. So we add wherever it is we have from our reference angle to 180 degrees. So that's how we note that. Then lastly, at the fourth quadrant, or for the fourth quadrant, we simply say, again, R is the same thing in all quadrants, but my theta polar for fourth quadrant will simply be equal to 360 minus the reference angle. Now, one thing to note is that your triangle, your reference angle, will always be with the x-axis. And since we're talking about a reference, we're talking about a right angle triangle rather, my reference angle will always be less than 90 degrees. So if it is less than 90 degrees, when solving for your angle, let's say for this part here, we'll always use positive signs, even if they are negative. Like for instance, when we're talking about the second quadrant, y is positive, x is negative. But when solving, because the calculator doesn't recognize or doesn't know which of the quadrants you are talking to or you are talking about, so it's always better to use the first quadrant. And then when you are trying to sketch, after sketching, you can now know whether you are subtracting it from 180 or you are adding 180 to it, or you are subtracting it from 360 to get your polar angle. Maybe we should try an example so this would make a lot of sense. So we've been given a point having -4, -7, and then we have to find the polar coordinates of this point. So originally it has been represented using our rectangular coordinate system or simply a Cartesian coordinate system. So first thing, finding r. So r will simply be equal to the square root of 4 squared plus 7 squared. The reason I'm neglecting the negative symbol is that by the time you square a negative number, it's always going to return a positive number. So 4 squared is giving us 16 plus and 7 squared would give us 49. So this will be equal to 16 plus 49. So that will be equal to 65. Okay. And then since 65 isn't a perfect square, we can leave our answer like this for now. So I'll just say 65 units. So since we're not giving any units, so just represent with units. And then we are done with our R. Now, also, like we said, R is not enough, or the magnitude of R is not enough to describe an object's location. We need the direction or the angle. So what we want to do is to make a rough sketch. Since we are given that my x is -4, my y is -7. So if I were to sketch this, I'll have something down below. So -4, that's negative x, negative y. So my point is somewhere here, which is 65. So if I'm to get my, what's it called, my triangle will look like this. Then I can now say tan of, so this time around, let's use psi reference will simply be equal to y over x. Note, I'm not using this y over x because they both have negative symbol and then to cancel out. No, we're saying that always use positive values, even if both of them are negative or one of them is negative. Always use the positive values here because your calculator will be calculating as if it is calculating values in the first quadrant. And since we're dealing with trig ratios, that is the highest angle we have in our triangle is 90, definitely our reference angle can be equal or more than 90. So always use positive values here. So we have y is equal to, so my y value is 7 over my x value is 4, and then this is my tan psi reference. So psi reference will simply be equal to, let me write that properly. So psi reference will simply be equal to tan inverse of 7 over 4. So let's do that using a calculator. So where's the tan? Okay, tan inverse. We have 7 over 4, and then this is equal to, so this is equal to 60.26. So that's now our answer in two decimal places. Now that said, so the next thing to do is to come back here and say, since it is in the third quadrant, so we know that my theta polar would be to add 180 to my reference angle. Okay, so this is simply 180 plus 60.26, and then I'll be having, so that's 240. Let's write that properly. 240.26 degrees. All right, so this is our final answer. I hope this makes sense. So we can say we can convert from what's it called, our Cartesian coordinate system to a polar coordinate system, and also vice versa. In order to convert back to our from polar coordinate system back to Cartesian coordinate system, then we make a use of, or we need the other ratios that we have. So I'm going to be writing it outside, and then we quickly do that here just to confirm that it is true, and then it works. So now we've only talked about the tan ratio. So we also have a sine. So we have a sine ratio. So sine of our alpha reference will simply be equal to, so for a triangle, we know if this is a triangle, a right angle triangle here, this is my reference angle, this is my x, this is my y, and this is my r. So we know that for sine, opposite over hypotenuse, so it becomes y over r. Then for cos, psi reference will simply be x over r. So if we're looking for y will simply be equal to r sine of psi reference, and then x will be equal to r cos of psi reference. So if you press any of these two back, we'll be having -4 and -7. So in your calculator, just press your, okay, so let's do for that of the y value. So my r value is root 65. So let's try and get that. Where's the root sign here? So root 65. Okay, multiply by sine of 240.26. So here we're having -7. So -7 for the y value, and then for x value, r, that is root 65, cos 240.26. Then we'll have what's it called, minus, okay, so -4. So that's what we are having. So sorry, this is not psi reference, this is theta polar. Let's try and clean that. So came in, okay, so it's supposed to be theta polar. All right, so let's just write that properly. So sine of theta polar, cosine of theta and polar. So here we can see how to convert from our polar coordinate system back to rectangular coordinate system. So now we're moving to the vectors proper. In physics, we talk about two types of quantities. We talked about the scalar quantities. So we said the scalar quantities are simple quantities that we describe with only their magnitude. For example, height, the density, length, distance, speed. So when we talk about all these type of quantities, we're only concerned about the magnitude. For instance, if I were to ask about your height, you wouldn't tell me your height is minus 5 meters tall. Because I'll be like, okay, are you growing downwards? Are you growing sideways? Are you growing, you know, abnormally? So it doesn't make any sense. So any quantity that we only describe with the magnitude, we refer to them as scalar quantities. And then for quantities that we require or that we describe using both their magnitude and also the direction, we call them our vector quantities. So why then do we need to study vectors as far as physics is concerned? To answer the question on the need to study vectors, we need to look at when we have these quantities, the scalar quantities, let's assume mass. So I know that I have the mass of an object, and then after putting the mass on a scale, I could read 5 kg from my scale. And then I added, let's say 3 kg on the same scale where the object of 5 kg is still present there. Then in total, I know that the total mass I will be having or that my scale will be reading will simply be the addition 5 kg plus 3 kg, and this will simply be 8 kg that is being read on my scale. But what if we have a vector, a vector quantity, let's say a force that is being applied on a box. So I have a box like this, and then I apply a force in this direction. Let's say this force is 4 newtons, and then apply a force in this direction. Let's say this force is 5 newtons. Now, if I want to add the total force that will make this box move, I simply cannot say 5 newtons plus 4 newtons. Now, the reason I can't say this is that both 4 newtons and 5 newtons are being applied at different directions. So in reality, without the essence of vectors, I wouldn't know the direction in which my box would move. So hence I can't come and add them algebraically like that. Hence the need or the usefulness of vectors in physics. So we have so many quantities. Some are scalars, some are vectors. And when we want to add them or subtract them or even multiply them, then definitely we can't just add them algebraically as if we are adding scalars or masses. So we need to look at a new concept, and that brings us to our addition and subtraction of vector quantities. But before we look at the addition and subtraction, let's look at vector notation. That is how we write vector quantities, how we denote them, how we write them as far as vectors is concerned. So the first thing we want to say, so let's say for instance, I'm given a force vector. So let's say I have F given as 160 newtons. Now, in order for me to write this vector, remember we talked about the Cartesian coordinate system, we also talked about the polar coordinate system. In terms of addition and subtraction of vectors, even multiplication of vectors, in as much as we are not talking about the components, then I always want to represent my vector using my polar coordinate system. So don't worry, this will be given to you. But I'm just trying to say polar coordinate system helps us a lot in our analysis on vector. So if you are given the magnitude, this force I've given, this 160 Newton, will simply be the magnitude. That is the length we just measured when we're doing the conversion from the polar coordinate system to the Cartesian coordinate system. So I need the direction here, and then the direction will simply be my polar angle. And then, so let's say we're giving direction, or my polar angle is 30 degrees to the horizontal. Now, if I want to represent this symbolically, Symbolically, I can simply draw my xy plane and say, now if I'm representing this symbolically, I'll simply say the length of my vector will be 160. So of course this is not drawn to scale, but let's just say this is 160. And then the direction that my vector is making with the x-axis is 30 degrees. All right. Now back to how we describe vectors. If we want to write a vector, first of all, we make use of the letter, a capital letter. In some textbooks, they write the letter like this. Some textbooks, they write F like this, they put an arrow on top. Why some textbooks, they just write the F to be bold. So if you write it like this, capital letter and then an arrow on top, or you write it in bold, or you write it in bold again and then still put the arrow on top, then we're talking about the vector. So know that this signifies vector quantities. We're talking about a vector, or we're trying to describe a vector. Now, the magnitude of the vector, which is this 160. So when they want to write it, they either write something like this. So again, faint letters, capital letter also, and then they put it inside a parenthesis, like two lines, two vertical lines. Either you see something like this, or they just write F without any bold symbol, without any arrow diagram on the top. Either you see this or you see this. Of course, we have so many other ways to describe them, but in most textbooks, these are the ways you see them using to describe or to denote vectors. All right. Now, for the direction, of course, they either use the theta, the alpha, the beta, and so on and so forth. So you'll be the one to know whether it is the polar angle they are given or the reference angle. So if it will be stated, so whether it is the reference angle that was given or the polar angle that was given. But if you are given a vector like this, the magnitude and the direction, so you know that this angle you are given is the polar angle, so not the reference angle. It is when you are given what's it called, or you are given a vector that's been resolved into its component already, that you have to look for its what's it called, polar angle, using the 180 minus alpha reference, or 180 plus alpha reference, or 360 minus alpha reference. All right. Now, symbolically, how do we represent a vector? We simply represent a vector by using an arrow. So let's say, for instance, vector F is 160 newtons. So just like I've drawn here, so I want to draw the same thing again. So this will be my 160. So I'm saying that if I were to take a ruler, then this line has been drawn to scale. The length of my ruler here, the length of my ruler will simply be equal to the magnitude of the vector, the length of this arrow that I've drawn. And then the tail end here, this is the tail end of my vector, that is where I'm coming from. And then this is my head, the head of my vector, where I'm going to. So this is how we represent a vector symbolically. Now, one thing about a vector is that I've drawn a vector. So this time around, I have to clear the screen so I can show this. Okay. We've drawn a vector, here. So that we've drawn a vector like this. Doesn't mean this is the only way to draw this vector. So sometimes when solving questions, we need to be able to rearrange or draw our vector in a different place to make our question easier to analyze. So what do I mean? So it means that in order for me to analyze my question properly, I can decide to take this vector F and then draw it somewhere else. I can consider my vector F is in the first quadrant here. So maybe in terms of analysis, my vector F being in the first quadrant wouldn't do much in my ability to solve a particular question. I can take the vector and then draw it in another place like this. Now, a condition is attached when rearranging or redrawing vectors in other places. we have to keep two things in mind and two things constant. The first of all, the length of my vector, and then second of all, the direction that it makes with the positive x-axis must be kept constant. So what we're saying is we can draw vector f anywhere. I can draw vector f here in as much as I maintain the length and also the direction. So if I maintain the length and the direction, I can draw vector f an infinite number of times in the plane in which I'm working at. So it doesn't actually matter. So this way of always taking our vectors and drawing them anywhere in as much as we maintain its length and also its direction is what what's it called, will aid us in analyzing questions, especially when we look at our triangular vector addition and also parallelogram law of vector addition. Now, one other thing to note, if I have two vectors, so let's say I have vector A like this, and I have vector B also in the same magnitude, that is, the length is the same and also the same direction. I can end up saying vector A and B are equal vectors. But then if I have vector A, let's say vector A is moving in this direction, and then I have vector B moving in this direction. So you can see that in as much as A and B are equal in magnitude, vector A direction is different from vector B. So I can say that vector A is simply equal to negative vector B. I can't say A and B are equal. So A magnitude definitely will be equal to B magnitude because it is the same length, but the direction would now be different. Now, moving on to the addition proper. So let's clear this and then we can now see how we add and subtract vectors graphically. So looking at how to add vectors together, so we're given a question. Let a vector be equal to 4 newtons, and where the angle, the polar angle is 30 degrees, and b vectors is equal to 6 newtons, where the polar angle is 120 degrees. So we have to find a plus b and then a minus b vector. So quickly, we know that, for its common logic, that when we add two numbers together, for instance 7 plus 3, the result will still be a number, so which is 10. Now, the same is true for vectors. When you have two vectors together or you subtract two vectors from each other, so you'll be having a vector. So that's why we can say that we said a plus b vector will equal to c vector, because the resultant, or what the result there, will also be another vector. So we want to call that vector vector c. And a minus b vector will give us vector d. So that's just our way of describing vectors. All right. So look at the first part, that is the triangular vector addition. Then before we move on to the parallelogram law of vector addition. And then for the triangular vector addition, it simply states that if two vectors are represented in magnitude and direction by two sides of a triangle taken in a particular order, then the third side of the triangle taken in the opposite order represents their resultant. So what does this mean? It means if I want to add vector A and B graphically, so what I can do by just making a sketch is to draw a cross like this, and then represent the two vectors I'm given, A and B, by two sides of a triangle taken in a particular order. So this order I want to take now, I'm going to draw my vector A like this after choosing a scale. So I will ensure that this angle here is 30 degrees. And this angle is 30 degrees. Now at the head of A, I'm going to do another cross like this, such a way that looks like this. And then I will draw 60, sorry, I said 6, 6 newtons. Then I'll ensure that my angle is 120 degrees. So do another cross that looks like this. So I'm just trying to make this a bit clearer. Okay. All right. So another cross that looks like this. So this is 120 degrees. And then I've taken this from this point to this point from here. So, okay. Sorry. Let me do that again. So this time more clearly. Okay. From here to here, 120 degrees. And then after connecting this, so we're told that the resultant will simply be from the starting point to the finishing point. So something like this. So this will be my what's it called, my resultant in this direction. So this is my direction here from the starting point back to the ending point. Hence the law we just stated. But if we are to solve this algebraically, what do we need to do? So first of all, our knowledge on geometry will be put to test here. Now, what do I mean? If this part here is 30 degrees from this point to my positive x-axis, so it means the remaining one in my first quadrant would be 60. And remember from geometry, if we are to have a line that looks like this, a transversal line that looks like this, and then I have two lines cutting in such a way that is like this, then what can I say? I can say the angle here will be equal to the angle here. So why is that true? Because they are vertically opposite angles. So that's the same thing I want to do in this particular place. So what do? I can say that this angle, this remaining 60, will be the same thing as this angle I'm having underneath here. So if this is true, then this will be 60 degrees, the angle underneath. Now if I come forward, upward, from this point to this point is 120. If I were to get the remaining angle on my line, on my pure horizontal line, that is, this is the line here, this is the what's it called, this is my quadrant, this is the line I'm having. So from this point to this point is 120. It means the remaining part here would be 60. How do I get 60? 180 minus 120, and that gives us 60 degrees, isn't it? But again, I still have a line here, the first line I've drawn, that is making an angle. This line here that I've drawn can say that here I'm having 30 degrees here, isn't it? So by 30 degrees here, I said the remaining one will be 60. So which is the 60 I've drawn here. So if this is 60 now, so this one is 60 degrees, then the remaining parts will simply be 30. So 60 plus 30, it means the angle I have in between these two lines should be 90 degrees. So remember, this is my A vector, that is 4 newtons. This is my B vector, that is 6 newtons. And then I have a right angle. So definitely this will be my reference, what's it called? This angle here will be my reference angle. So let me call it beta reference. But remember, we said for using our graphical approach, since what's it called, the length of this line from this point to this point will be the magnitude of my C vector, and then the direction will be from this point, the positive x-axis, to where this line is actually touching. So if I can find the angle inside of this triangle, I'm going to add it to 30 degrees, and then that will be my polar angle for this question. So let's see, what can we do? Now, because it is a right angle triangle, then I can easily use my Pythagoras theorem to find the third side. If it is not a right angle triangle, then I have to use my cosine rule or sine rule. So you can even use the cosine rule for this question. You have the same what's it called? You have the same answer if you've done it properly. All right. So Pythagoras rule, we simply say R will be equal to, or sorry, I said R. So since we're using C, I can say C is equal to square root of 4 squared plus 6 squared. So what is 4 squared? 4 squared is 16. 6 squared is 36. And 4 squared, that's 16 plus 36. That will give us, that's 52, 52, yeah. So anyway, so this is my C magnitude, C magnitude. Now, for me to get my direction, the direction, remember a vector is not complete if you've not added the direction. It's only magnitude we are using to represent the vector, then it's not complete. We also need the direction also. So for the direction part, what do we do? So we simply go back to our question. So B vector, I'm going to take B B as my, what's it called now? I'll take B as my y and then A as my x. So my tan of, what's it called? Tan of my angle, this angle here, will simply be equal to 6 over 4, and psi reference will simply be tan inverse of 6 over 4. So 6 over 4, that gives us, what's it called? Or tan inverse. So let's do that using our calculator. Tan inverse of 6 over 4. So that will give us 56.31. So remember what we said, we're going to add it to this initial 30. So adding to 30, so we can say plus 30. Then my polar angle will be equal to, that's 86.31. So it's 0.31 degrees. So this is how we had vectors together using our triangle law of vector addition. So I hope this is clear. So how about we subtract? So for subtraction, so we are given the same question. You know what our vector is, you know what our vector b is, and then we are given the polar angle. So like we said for addition of vectors, we know that when we add two vectors together, the resultant or the results will be another vector. So also when we subtract two vectors from each other, the resulting or the resultant will also be a vector. So quickly let's sketch and then we'll see how we can analyze our solutions to our question. So looking for vector A minus vector B. So sketching this, again, I'll do a small cross like in previous example. Then small cross represent vector A. So vector A is vector A here. Okay. Then at the head of vector A, draw vector B with an angle of 120 degrees. So we have vector B moving in this direction. All right. Now, if I were to join the start to finish, I'll be talking about A vector plus B vector. But since we're looking for A vector minus B vector, I'm simply going to change the direction of my vector B. Remember, we talked about equal vectors when we're talking about vector notation. Two vectors are equal only if their magnitude and direction are the same thing. So, but if two vectors are equal in magnitude only, then we can say A vector will be equal to negative B vector. So definitely I want to switch this or I want to reverse this by 180 degrees in such a way that instead of going up, it will now come down, maintaining its same length. Then finally, I can now connect these two lines together. So from start to finish, this is A vector, this is B vector, then this is D vector, which is simple as saying A minus B vector. So I hope this makes sense. So when we're done now, we can now start using our knowledge on geometry. So remember from geometry, we know that our A makes an angle of 30 degrees to the horizontal. So this is 30. Let me write that properly. So this is 30 degrees. So definitely the remaining part here will be 60 degrees. And if this is 60, this also will be 60 because they are vertically opposite angles. All right. Now, if from this point to this point is 120, then definitely this remaining part here will be 60. So why is it 60? The angle on a straight line must be equal to 180 degrees. So this is still a straight line, and what's it called? So we simply say 180 minus 120, and that will give us 60 here. So if this is 60, definitely the remaining part here would be 30. So I know that the angle between this triangle here is 90. So if it is 90, then definitely it is something as saying a right angle triangle. Now, A vector has a magnitude of 4, B vector has a magnitude of 6. So if I were to draw my triangle outside the sketch, I know I have a sketch like this that looks like this. So this is 6, this is 4. Okay, so this is the angle I'm looking for. So because my theta polar or my polar angle will be from the positive x-axis to where my vector D is starting from. So that's the angle I'm looking for. So what we just want to do is like a map of our final angle. So let's say how we're going to be getting from this angle here back onto this place. So since my line is in the fourth quadrant and anything I'm getting, I'll be subtracting it from 360. So after applying our knowledge on Pythagoras theorem and SOHCAHTOA, I'll get the total angle in my triangle. I'll get the total angle in my triangle like this. But remember, I already know that part of that angle is 30 degrees. So subtract the total angle from 30 and then subtract that remaining one from 360. So that will give me the angle on my theta or polar. So R or D vector rather, the magnitude of D vector, so magnitude of D vector will simply be equal to the square root 4 squared plus 6 squared. So this is the same thing as saying 52 units, just like the previous example. Uh, so we can now, what's it called, look at how to find the direction. So I'm just going to remove this part of the, I'll remove this part of the screen and then try and walk towards there. Okay, so for the angle now, so I'm going to be making use of my tan ratio. So tan theta will be equal to, so again, I have 6 over 4, isn't it? Okay, so theta now will be equal to, so tan inverse of 6 over 4. So tan inverse of 6 over 4, so let's quickly get the calculator and then let's see what we're having. Tan inverse 6 over 4. Okay, I need to get a proper calculator. Tan inverse shift tan 6 over 4. So we're having 56.303, 56.3099. Okay, so we're having 56. So where is it? This is equal to 56.30. Okay, so let's just say 56.31. So to make it to decimal point degrees. So this is the total angle from this point here to this point. But since I know that from here to here is 30, so the remaining one will simply be 56 minus 30. So minus 30, so that's 26. So I can say minus 30. So this will be equal to 26.31. Then I'll now subtract this from 360. So 360 minus answer should be having, so my theta polar will be equal to 33.690. So 33.690 degrees. So what's in the magnitude? The magnitude was what? 52. The magnitude, then the angle is 33. No, sorry, this should be 333.690, not 33.690. So I hope this is clear. So this is how we add and subtract using our triangle law of vector addition. Okay, so moving forward, we'll be looking at the parallelogram law of vector addition. So for the parallelogram law of vector addition, so we start by stating the law. That is, if we can represent two vectors in magnitude and direction by the adjacent sides of the parallelogram, then the diagonal of the parallelogram drawn from the point of intersection, if the two vectors are starting from the same point, represents the resultant of the vector in both magnitude and direction. So what this is simply telling us is, remember when we talked about the triangle of vector addition, we said if we can take two vectors and represent it with two adjacent sides, of a triangle, and then of course our representation is both in magnitude and also direction, from head to tail. Then the top side of the triangle, drawn from the origin, that is from the point of starting, will now be the resultant. But for parallelogram law, we're saying the two vectors now start from the same position, and then if they're starting from the same position, represents the two vectors both in their appropriate magnitude and then their appropriate directions. And at the end of the day, we complete our parallelogram, and then our resultant will now be represented both in magnitude and direction, drawn from the point of intersection. So, moving on to the same question we solved using our triangular vector addition for. So we're going to be solving the same thing, and then we'll see if we arrive at the same answer. So this time around, instead of drawing small crosses, we're going to draw a bigger cross. I'm going to draw it at this side so we can have more space to work underneath this. So let's say we have a big cross like this, and then I'm going to try and represent the two vectors I'm having, A and B. So represent A first. So A, if I can represent A, of course, if this was a graph, I would have chosen a scale, then use my ruler, my protractor, measure the angle of 30 degrees, and with my scale, draw a line of 4 meters, 4 centimeters, depending on the scale you've used on your graph book. All right, so 4 centimeters, obviously. So this is my 4 newtons with an angle of 30 degrees to the positive x-axis. Okay, now I want to represent the second vector, vector B. So I'll simply draw vector B starting from the same origin. So of course, let me define this a bit. Okay, so this is vector B. Now remember what we said about vectors, that we can move them from anywhere in our plane in as much as we maintain its magnitude and direction. So instead of joining these two lines together, we're not going to be doing that, but instead we're going to be redrawing vector A and B at the head of each of the vectors that we're having here. So for instance, if this is vector A, I want to shift vector A, that I can draw the same thing, maintaining the same angle of 30 degrees to the horizontal. If I were to draw an horizontal line here, you see that it's maintaining the same 30 degrees like this, and then draw my vector B to this point, maintaining the same 120 degrees to the horizontal. So when I'm done here, then the last thing to do, as the law implies, the diagonal of my parallelogram would now be the resultant. Diagonal, to draw a line like this, so from this point to this particular point, and then this diagonal will now be the resultant of my vectors, that is the addition or the subtraction. But for subtraction, we look at a different principle, but for now, let's just stick with addition. So we can call, since we say let's A vector plus B vector, let's represent C vector, so I can just write C vector here. Okay, and then this is my B vector. Okay, this is my A vector. All right, so now it's time to solve using our laws of triangle, that is the Pythagoras theorem, SOHCAHTOA, cosine rule, or sine rule. All right, so first of all, let's apply our knowledge on geometry. So we know that if this angle from this point here to where A is starting from, if it is 30 degrees, and then from this point to where B is starting from is 120 degrees, then the angle I have inside of my parallelogram will simply be 120 minus 30. So this big angle here I'm having inside of my parallelogram, if I were to draw the parallelogram outside like this, pardon my sketch, so this big angle will simply be 120 degrees. But since I'm dealing with a diagonal like this, so I don't know how exactly this angle is being divided. But one thing we know about parallelogram is the adjacent sides of a parallelogram are always supplementary. That is, when you add them together, they will always be equal to 180 degrees. So if this is 120, so it means, or it must mean, sorry, I said 120, this is 90 rather, not 120. So because we said 120 minus 30. If this is 90, it must mean that this other angle here must be equal to 90. Because by the time we subtract 90 from 180, the result we have is also what? Also 90. So we can take this triangle outside. Take this triangle outside and sketch what we have. So this is angle 90. This is my vector B here. This is my vector A that brought up at this particular stage here. So this is 90. All right. So we don't know this angle here. All right. We also don't know this angle here. Now, one more thing that we want to know, since my resultant will be if I was solving graphically, I will simply take my ruler, measure the length of this line, the diagonal. That will be my magnitude. And then the direction will now be from positive x side to where my diagonal is starting from, to where the line is. So this angle is what I'm looking for. So you can see that I know this angle from this point here to where A is starting from, which is 30. So if I can get the angle inside of this triangle, this other triangle here, if I can get the angle, then definitely I'll just add it to 30, and that will be the angle of my resultant. But then how do we do that? Since we have two triangles here, so we can see that from geometry, this angle that is here, this one I'm shading here, will be the same angle as this one that is here. Why? Because they are vertically opposite angles. So if this is x, this also will be x. This one will be the same thing as this small one here, but we're not bothered about that. So that means after solving for what's it called? After solving for this angle here, after solving for this angle, let's call this angle theta. Then I also need to find this other angle because this is my major point of concern as far as getting my polar direction for my resultant vector is. So let's go into the solving. So vector A, so since this is a right angle triangle, so for me to get this vector C, so obviously it will be the same thing because we've done something like this before. So C will simply be equal to, the magnitude of vector C will simply be equal to square root. So vector A, given that it is 4 squared plus vector B, 6 squared. So this is equal to square root of 52 units. Okay, so same thing like we got in the previous example. And then if we're looking for this angle here, so we can either find this angle first, then take the summation and subtract this angle from 180. But instead of doing that, why not let's switch the triangle? So we switch it in such a way that this now becomes my opposite side. Instead of A being my opposite side, B becomes my opposite side, and then A becomes my adjacent side. So remember, the tan ratio is always opposite over adjacent. So I can say tan of theta of, okay, so since I've used theta here, so let's just say tan of alpha would now be equal to 6 over 4, and alpha will be equal to tan inverse of 6 over 4. So let's write that in our calculator. So let's see what we have. Tan inverse of 6 over 4. So we're having 56. This is equal to 56.31. Then that's not all. Since we've gotten this angle here, so we already know that this angle will also be the angle of this side of the triangle. So we had it to 30. So we just simply say plus 30 degrees plus 30 degrees, and then this will be 86.31 degrees. So you can see we're having the same magnitude and also the same direction as when we use the parallelogram law. So in an exam, if it is not specified, you have the luxury of picking whichever method you feel more comfortable with. Maybe it is the triangular vector addition or the parallelogram law of vector addition. But note you should also be able, if you are able to apply the laws, you should also be able to state the laws even from your mere sketch. All right, so let's quickly look at how to use parallelogram law to subtract vectors together. All right, so for this time, I'm going to clear this away. Okay, clearing this. Okay, and also I will clear this too. Okay, all right. So now let's say we want to subtract this. So what do we do again? We draw a big cross. We will draw a big cross. Remember now we're looking for a minus b. So draw a big cross, and then we draw vector a starts from here, from the origin, making an angle of 30 degrees to the horizontal. We draw vector b starts from here, from the origin also, making an angle of 120 degrees. Now, when we're looking for a plus b, we completed our parallelogram. But if you're looking for a minus b, so instead of completing the parallelogram now, we're just going to be joining b to a. So the head of b to the head of a. But there's just a simple problem. Since we know that a vector has both magnitude and direction. So how do we know which direction we will be having? So this is my vector a, and this is my vector b. So we'll go back from our knowledge on um, 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 motion in one dimension. So when we said final minus initial, so let's come and look at this. A minus b, what do we think will be the final? Definitely A will be the final, A vector will be the final, and B will be the initial. Remember, change in position, but changing from B to A. So it means A is my final position and B is my initial position. So my arrow will come in this direction. So I can just do a small cross here, and then my, okay, so let me do the cross properly. The cross like this, okay. All right, so and then my arrow or my direction will simply be from this point here back to where this is. So you can say, so we've done something like this previously using our law of triangle addition of vectors. So you have definitely have the same results. The only tricky part is in getting the angles here. So if you are extremely good in geometry, then this shouldn't be a cause for alarm. All right, so this is all we have for, or this is all I have rather for today's video. In our subsequent video, we'll be looking at how to use resolution of vectors. So where we resolve vectors into its components I and j, and also k, to use to solve. So and then you have three different ways of adding vectors or subtracting vectors. Then after that, we'll talk about multiplication of vectors. So if this video has been helpful to you, please do well to share with your colleagues, your classmates, your siblings, and then you can also subscribe to the channel and like the video so that when I release more new content, so you'll be the first to know. Thank you and bye bye.